So the first thing that I want to mention is to introduce very basic ideas about the model. So we're dealing with phase-coupled oscillators. The oscillators may have identical frequency or equal frequencies or maybe different frequencies. We'll talk about those different cases, but they are characterized by a coupling function, G, which is shown here. And in the continuum model, in a continuum limit, this system is described by a non-local partial differential equation of this type, where the coupling kernel is up to you. You can choose how the oscillators are coupled. You have that sine theta x minus theta y. And then in addition, what we do is we introduce a phase lag parameter alpha, which is very important for the generation of partially coherent structures, of which the chimera state is the canonical example. And I'm showing here in the figure oscillators just on a ring, and the phases are shown in the vertical direction. You can see that some of the oscillators are synchronized. For example, in this region, the other oscillators oscillate in an asynchronous way. And we're interested in properties of these partially synchronized structures, where you have coexistence between coherent structures and incoherent structures. And the interesting thing is that these things exist even when all the frequencies are the same. And that was the initial surprise. I think it's not so surprising if you have heterogeneous frequencies that you might get partial coherence and partial decoherence. So I'm going to I have all these other things here. Maybe I can close this. So how do we think about the 1D system? Well, I'm just going to review a few properties of the 1D system because most of the lecture is going to be about two-dimensional arrays of oscillators. But in 1D, things are relatively simple. We can define a local order parameter, which is called little z here. And it's just a local average over the order parameter that we heard about from the previous speaker, e to the I theta. And then one can construct a differential equation, an evolution equation for this local order parameter, and that takes this form over here. So this is a partial differential equation, and it's a non-local, nonlinear equation, because it includes not just z, which is the local order parameter, but also this quantity capital Z, you can see over here, which is the convolution, which is the convolution of the order parameter little z, the local order parameter with the coupling kernel, and as defined here. Okay, so that is the basic equation that we're going to be studying. Here it's written in 1D, but we're going to generalize this to higher dimensions in a moment. And these types of equations have particular types of solutions that oscillate in synchrony like this with a global frequency at capital omega. And if you want to study states of that type, you can substitute this ansatz into this equation, and you get a nonlinear, non-local equation of this form. And this is a nonlinear eigenvalue problem for this global frequency capital omega. And notice that it depends on that phase lag parameter alpha that I introduced on the previous slide. Now that equation that I've just shown you, this is actually you can think of this as a quadratic equation for z tilde, the local order parameter, and you can solve it as a quadratic equation, and then you get a solution that looks like this, or like this, depending on whether this quantity mu is a real quantity or imaginary quantity. And then you can construct this convolution, this capital Z that I've mentioned. You just take the convolution of these expressions with the coupling kernel, and that is going to be what I'm calling the order parameter of the system. When R is equal to 1, that's going to correspond to the coherent region. When R is less than 1, that's going to correspond to the incoherent region. So that is the kind of general structure of these types of problems. And this equation is called a self-consistency equation. And it's basically what we've heard in previous lecture. It's derived by Ott and Antonsen in this slightly more complicated question. So our questions here are, we would like to understand First of all, when these chimera states, these partially ordered states exist, we'd like to be able to do bifurcation theory for them. And very nice work has been done by Hayato Chiba, for example, that I mentioned there. The difficulty with doing bifurcation theory for these kinds of problems, and that was recognized by a number of people, including Crawford, we heard that name before, is that the linearized problem has a continuous spectrum. But there are ways of getting around this, and that is to make specific choices of this coupling function, and in particular, choosing harmonic functions for the coupling function is very helpful because it reduces an infinite dimensional problem to a finite dimensional one. So just very quickly, this is what the linear stability problem would look like for this particular case. It's a non-local but linear stability problem. This V, again, is this convolution that we already saw before. And problems of this type have solutions that grow exponentially with the growth rate lambda. And you can substitute this ansatz into this equation, and then you can solve it explicitly. And this shows what the eigenvalue plane looks like. Real part horizontally, imaginary part vertically. And you see the continuous spectrum. That's not going to be of interest in this talk. What is going to be of interest are these point eigenvalues that can emerge from the continuous spectrum on the imaginary axis. And that, of course, indicates the onset of instability as soon as this eigenvalue emerges from the continuous spectrum. So here's a typical calculation. Here's the point eigenvalue as a function of this parameter beta. Beta is pi over 2 minus alpha, because that's a convenient parameter, because as I mentioned, these chimera states are generally found for alpha close to pi over 2. And you can see that, for example, in this case, a two-headed chimera with two synchronized regions becomes unstable at this critical value of beta, and then the system evolves due to an unstable eigenvalue for larger values of beta. So I'd like to do something similar to what I've just described in the 1D case, particles on oscillators on a ring, but now looking at a two-dimensional array of oscillators. So imagine points in the XY plane. At every point you have an oscillator. And then there's a variety of different structures that can form these partially coherent structures. So here is a stripe chimera state on the left. In the middle is what we call a twisted chimera state. Here is a spot chimera state. These chimera states could be either that you have a coherent region like this spot in the middle and it's embedded in an incoherent background, or vice versa. You can have an incoherent spot embedded in a coherent background. Here are the states that I'm particularly interested in this talk, and these are the so-called spiral waves, spiral chimeras. And you can see, if you look carefully, that there is an incoherent core in the center. For other parameter values, that core may become larger, and it's surrounded by a coherent region in the form of a rotating wave. So the wave rotates in this clockwise direction around this incoherent core. And you can get these multi-core states, like this 4-core state, and we're going to be hearing more about that in just a moment. So those are the kinds of structures that I'm interested in. Now, these structures have been seen in some experiments. My favorite experiment is this one by Jan Todt with Showalter, where they take little glass spheres. They fill it with the Bielosov-Zhabotinsky reagent, so each little sphere represents a chemical oscillator. They put them in a plane, and then they synchronize them through optical means. And when you do that, you find structures that are a little bit like the numerical simulations, but you do see these kind of spiral waves with an incoherent core. You have perhaps a less good example over here. Sometimes they can break up as time increases. Sometimes they can start moving. And I'm going to be particularly interested in these traveling chimera states. So let's talk about two-dimensional arrays of these phase oscillators. So this is an example of what I mean. So this is the discrete version of the problem. So these indices J and K label locations of the oscillators in the x direction and locations in the y direction. Here are the frequencies of each of these oscillators. Here is this coupling function that I already mentioned, and here is that important phase lag, okay? So that's obvious generalization of the 1D case. And we're going to be interested in coupling functions, that depend on separation between the oscillators. And here is the first important assumption, and that is that we're going to use one of these harmonic kernels. And here is a kernel in 2 dimensions, cos x plus cos y. And then there are harmonics whose magnitude is measured by this parameter gamma. So this is a 1-parameter family of kernels. And one of the things we'll be looking at is what happens as you vary gamma, introducing these higher order harmonics. Now, you can do the same continuum limit that I've described in the 1D case, and you get this kind of equation. And here, all the frequencies are the same, because I'm, for now, looking at identical oscillators, okay? Here is that coupling kernel that I've introduced over here, and then you have the same sort of terms beyond that. So here is what you get when you solve this problem. So this is a 4-core chimera. You can see the 4 incoherent cores, the waves around them, the laminar waves or synchronized waves rotate clockwise around this one, counterclockwise around this one, and so on. And you can generate, for example, more complicated structures like these 16-core states. Now, stability and existence and stability of these kinds of structures. So in the case where gamma is 0, so I'm looking at the coupling kernel 0 with just cosine x plus cosine y, the order parameter, that self-consistency equation, has solutions that are very simple. It's just b times sine x plus I sine y, as you can see here. And when you take this solution and you substitute into the self-consistency relation that I obtained earlier, you get this perhaps complicated looking equation, but this is an equation that has a real and imaginary part, and you solve it for 2 quantities. And what are the 2 quantities you want to know? You want to know this quantity b here, and you want to know that frequency omega. That's the global frequency of the oscillators going around together. That's their common frequency. And so here is a typical solution. Here I'm varying that phase length parameter in terms of beta here. And you can see B in green here as a function of beta, and the overall frequency in red over here. And on the figure on the right, you see the fraction of the oscillators that are synchronized, that are coherent. It starts at 1 when beta is 0. That's alpha is pi over 2, and then it decreases with increasing beta. This crossover point is interesting because the type, the argument of the square root changes type. That has some consequences, and the consequence that it has is that you transition from a situation where you have incoherent regions embedded in a coherent region to the other possibility, and that is that you have coherent regions now embedded in an incoherent background. Now, what about stability? Well, we can play the same kind of game and linearize about that solution that I've just found, and you get this non-local linear problem, and that can be solved. And the reason these kinds of problems can be solved is because they are fundamentally finite dimensional for the choice of coupling kernel that I have made. And so here you see in black as a function of beta a point eigenvalue, a real point eigenvalue. This one corresponds to folds. And then in blue you see 3 bifurcation points, beta 1, beta 2, beta 3. These are Hopf bifurcation points. And if you put all these kind of results together, you get a picture of what happens in the parameter plane. And the parameter plane is this phase lag parameter beta plotted horizontally. And that parameter gamma, remember, which includes the high order harmonics in my coupling kernel, plotted in the vertical direction. So shaded here in blue is the case where I have a stable 4-core chimera states. Here in blue are the Hopf bifurcations. In black is that fold bifurcation. And these symbols here represent results of numerical simulations just to confirm the predictions from this analytical theory. And you can see the kinds of structures that emerge, when you cross from the stable regions. In other words, when the four-core chimera state loses stability via a Hopf bifurcation, for example, you get structures like this. We're going to look at these in a little more detail in just a moment, but you see a whole variety of different states that emerge from this kind of stability analysis. This black region here is a disconnected region of 16-core chimera states. So let's look at one of these cores, and what you see, and I think this is an interesting observation. You have a boundary of this incoherent core in a dashed line. That corresponds to r equals 1. Outside that region, r equals 1, and you have the coherent wave going around this core in this clockwise direction. But inside it, you see the appearance of these filaments, and these represents little regions of coherence appearing inside that incoherent core. And they appear because the eigenfunctions of the Hopf bifurcations are singular on a certain curve that you can calculate that lies on this dashed curve. And you can see what effect it has on the frequencies, the average frequencies at different distances from the core. And you can see here, you have a coherent region, then you have an incoherent region. But at this region here, which is when you're crossing this interior dashed line, you see a little bit of synchronization over here. You'll see that a little more, I think, in the next few slides. So this is a consequence of the fact that my chimera is now quasi-periodic, right? Because remember, you had oscillatory states with these global frequency. That state has lost stability to a Hopf bifurcation, introducing a new frequency. And that new frequency is detected by looking at, for example, the behavior at two neighboring oscillators in the lattice, like this point x and a nearby adjacent point to that, and you can see the appearance of the new frequency in a direct numerical simulation. And here you see the autoparameter and the corresponding phase of the autoparameter, kind of to complete the description of this state. Now, as you vary the parameter beta, you see a whole variety of these kinds of structures appearing via the same process, via the introduction of the new frequency through these Hopf bifurcations, together with these filaments that represent synchronization, if you like, within the coherent core. And again, this represents the autoparameter, the real autoparameter, modulus of big Z, and this represents the phase of big Z. And if you look at one of these cores, if you have three filaments, they are at distinct distances from the core, and then you average the frequencies going around, you see this kind of step-like structure. Each filament is responsible for a jump in the frequency, and you get these additional synchronized regions inside the core. So that was the case of identical oscillators. That is an interesting and important case, but it has one consequence, and that is if all the oscillators are the same, then these chimeras cannot move. And the reason is that that contour mod Z equals 1, or the contour that bounds or separates the synchronized region from the desynchronized region, has to be stationary. So that's a mathematical result. But we can depart from that by introducing heterogeneity into the frequencies. And so that's done over here through the use of a Lorentzian distribution, is GW. We choose a narrow Lorentzian distribution for our problem. And then for the coupling kernel that I'm going to use, I'm going to just pick a top hat kernel. So all the oscillators within a certain radius, sigma, are coupled, and all the oscillators that are further separated are uncoupled. Okay, so that's a typical kind of thing that people have been using. And again, I'm going to be using this parameter beta to describe what happens in this case. So the interesting thing about this case is that now the structures can move. And so here is a two-core chimera state. This is in terms of the modulus of the order parameter. You can see the incoherent cores, and the incoherent cores travel together like point vortices, like we heard about from Ramakov-Indirajan. And so here is the corresponding phase of those point vortices. Now, these structures don't have to be identical. And for example, you can have two distinct states, and they follow these black lines. And this is the corresponding phases. Or they can actually do this kind of corkscrew motion, one basically following another one. So the whole variety of states that have been found simply by doing brute force numerical simulations of this kind of system. And that work is reported in this paper by Martin Bataille. So we would like to understand, how to describe this moving structure. What can we say about their stability and other properties of these kinds of states? So we're going to use the same procedure. We're going to take this continuum limit, and that, of course, leads to the Ott-Antonsen equation for this problem. So it's written here. The difference now is that I have this extra term. It's a damping term. And the coefficient of damping is gamma, is the width of that Lorentzian distribution. And again, I remind you that this capital G is just the convolution with the coupling kernel. And so you might say, well, let's look for these, the simplest situation is I have these two incoherent cores and they're traveling together like this. So let's look for a solution where Z is some function A, which is a function of y minus st, so s is going to be the speed of the state. And then, of course, you have this global frequency, capital omega, which you also have to solve for. So now you have to find two things, right? You have to calculate the speed, and you have to calculate this global frequency, omega. So this is the type of result that you get from doing these calculations. So on the horizontal axis, I have the phase lag parameter alpha, and on the vertical axis I have the speed. When alpha is 0, the problem is variation, so these structures cannot move. But as soon as alpha departs from 0, they start to move, and initially they move very slowly over here. Then you enter more complicated regions. I'll talk about this in a bit. And then you get this region of slanted snaking, so-called, which is a property of the fact that this is a non-local problem. And then you get a whole bunch of other states up here. So in this picture, the important thing for our purposes are two things. One is that we can do numerical continuation of these states. So we can compute both stable and unstable states. And we can also compute their stability properties. And the dashed lines indicate that the solutions are unstable. The solid lines, like here, indicate that the solutions are stable. And this is the kind of thing that you can do because of the methods that we use. So in region 1, this just shows a few examples of what some of these stable solutions look like. On the left, you see the modulus of the order parameter. So you can see these arc-shaped filaments. These are there, by the way, because the state is moving and oscillating, right? So it's a similar mechanism to that quasi-periodic but stationary state that we saw earlier. Here is the corresponding argument. And so on. So you can see that you get these very complicated structure that you can compute numerically. Now, these numerical calculations were very, very expensive because when you do numerical continuation, you have to calculate the Jacobian matrix. The Jacobian matrix for these kinds of problems are full, so inversion is very costly. And so we have spent a lot of time trying to simplify, these kind of computations. And I want to say just a couple of words about that. The general structure of this problem is this, right? I have to do these convolutions. The coupling function in general can be written as a Fourier series with the corresponding inverse, as indicated over here. But an interesting and useful approach is to truncate that Fourier series. And of course, you're not going to get a top hat function from a truncated Fourier series, but you get a reasonable approximation to it. And we have found this particular coupling function very useful. So again, I have the cos x plus cos y. The amplitude of that term is a. The leading order term is 1 here. And then we have this product, cosine x, cosine y, with a coefficient b. And you can compute what these coefficients are for the top hat kernel, and you get some values of that, which I'll talk about later. But those values, of course, depend on the radius of the top hat kernel. So here is our equation that we want to solve. We are interested in finding this solution A of x and y. This is in the case alpha equals 0, so these are stationary solutions. We write down the self-consistent equation. There's no alpha in this equation because alpha is 0. And then we want to look for bifurcations. So here is what we find for the case alpha equals 0. And you see here the plane of those coefficients in that truncated Fourier series, that coefficient capital A and the coefficient capital B. And you see a number of different regions that contain stable solutions. Outside, all the solutions are unstable. And numerically, when we do simulations, we find indeed that inside these regions, you find stable solutions. And here are some pictures of those solutions that we obtain. And so you can have solutions, for example, that are aligned this way. They could be aligned along a diagonal, and they could be asymmetrical like this. And so these are the types of solutions that you find. In the case beta equals 0, this is what the order parameter as a function of A would look like. So this is for B equals 0 and alpha equals 0. And so here is the primary, so this is the incoherent state. Here's the primary branch. It generates a kind of line incoherent region here. And then there's a number of secondary bifurcations that we predict, and we can follow the branches that appear in those bifurcations. And the solutions that we find are shown over here. There is a four-core state. There is a different type of four-core state with different symmetries and so on. Now, when you make beta B not 0, you get much more complicated bifurcation diagrams. This is essentially done semi-analytically. And of course, now the states you get, are a little bit different, of course. B is not 0, but here are some sample solutions that you obtain from this approach. So how do we actually do these calculations? I'm going to just say a few words about that. So suppose I want to just look for solutions that travel in the y direction. So I want to look for a solution of this type. I substitute that into the Odd-Antonsen equation, and I get something of this form, right? It's a partial differential equation. The W here is given by that convolution that we talked about earlier. So suppose that for every W and every fixed X, this profile equation, that's this equation, has a 2 pi periodic solution with a modulus of A less than 1. So that means you have some incoherence in the problem. That solution, of course, is generated by an operation that you perform on this W, and in the self-consistency equation tells you what that U has to satisfy. So that is schematically the equation that you have to solve. Now it turns out, of course, that this equation is a Riccati, it's a complex Riccati equation, right? It has this quadratic term here. And so there are some tricks that can be used to study equations of that type. One of the things you find for an equation of this form, that the unit disk that's the region of incoherence, is an invariant set of this equation. And then you can look at the Poincaré map of this equation, and that is given by this Möbius map. So that goes back to some work of Steve Strogatz. Now, you can show that whenever this parameter xi is not a purely imaginary number, then you have a unique 2-pi periodic solution, z of t, of this problem, and that use that fact to accelerate this numerical continuation that we perform. And the way we do that is we solve this Riccati equation with some initial conditions. We do it for 3 distinct initial conditions, and that's enough to determine the coefficients in that Möbius transformation. And once we have the Möbius transformation, I have the Poincaré map, as I mentioned on the previous slide, and then we just look for fixed points of that Poincaré map. And so this obviates this whole problem of having to invert these full Jacobian matrices for the continuation problem. We just follow fixed points. So that's how we do the calculation. And this is the type of result that you get for our truncated Fourier representation of the coupling function is 1.8 and b.3. So these are close to the values that we found for the top hat kernel, and you get a picture that looks like this. There's a whole series of very interesting transitions as you increase alpha from 0, and the structure starts to move. This is in the moving reference frame, so you don't see the motion here, but you do see the appearance of these subsidiary filaments associated with this kind of quasi-periodic motion, the fact that it's periodic and translating, and you get this kind of picture. And this is very similar to what we found in the original top hat results. And I just emphasize at the end that if I change my values of A, for example, to 1.9 or to 0 or 2.1, I get very different tracks in this speed of the solution as a function of alpha. And so that suggests that this truncated Fourier representation is actually pretty good at capturing the behavior of the top hat kernel that I mentioned at the beginning. So here is a quick summary. We have seen that spiral chimeras can undergo spontaneous motion. In the case where I have heterogeneous oscillators, with at least in the case where the frequencies are drawn from this Lorentzian distribution, we can compute the speed of such states and their stability through the techniques that I tried to explain. And I've shown you that the results agree actually very well with the direct numerical simulations. And so here's a couple of pictures that I've shown that summarize the main results of the study. And then there's a couple of references at the end. So thank you very much for your attention.
If you have an odd coupling function, like sine.
Oh, if I don't have the sine coupling?
You have sine coupling, not cos. Like x minus, I minus j, you take sine of that instead of cos. In that case, the function will be odd in the sense right hand side is positive, left hand side is negative. If such a coupling exists, will there be differences?
Are you talking about the solution? Sorry. Are you talking about the solution of the self-consistency equation?
No. I'm just very initial slide, g of xy.
No, that's that's just a translation. It doesn't do anything. I can just translate the origin of x and y, and and I can make a sine into a cosine.
No, this distance from a given site, okay, distance from a given site, how will you translate it? I mean, you have different oscillators at different places, right? One is at site 5 and another is at 7. Okay, 7 minus 5, and then 3 minus 5. Okay, one is 3, one is plus 2, and one is minus 2. Their g of xy will have different signs, isn't it? You can't translate. Coupling function being, maybe I have understood.
Yeah, I'm sorry, I'm not quite following what you're trying. Maybe we can discuss that privately.
Any other questions? I have one quick question. So
Yeah.
this curve is so bumpy. So what is the origin of such bumpy structure?
Thank you for that question. So the origin of these bumps has to do with the appearance of additional filaments. These, if you look,
I see.
maybe I should put it, I'll show this on the previous slide here. It's a little bit bigger. But you can see that the number of filaments is changing as you follow the curve. And each time you go through 2 folds, you generate a new filament. And that's very typical of the behavior of localized structures in dissipative systems.
Thank you.
And it's slanted here. These structures are slanted because of the non-local coupling in the problem.
Yeah. Okay, thank you. Any other questions? Okay, if not the case, let's thank to the speaker again.